Okay, so welcome everyone. So today's session we will be discussing on a few things. So we are now, as per the sessions, we are in week 3, and I understand that we are, I think, lagging by a week's time for some reason. So, so what we will try to do now is most of the sections on this engine performance. We have posted 3 videos, uh, as you can see in the announcement section, like I think yesterday. So I would request all of you to go through those videos on learning how to do engine performance calculations. So today, first we will be looking at continuing the discussion on electric vehicles, which we started last time, and then we'll quickly move on to some more discussion, again using the class notes on supercharging and combustion in spark ignition engines. So in the next week, I think we will move on to looking at automotive powertrain slightly, and we will start taking a look at transmission. Once we come to braking, I think braking will be significantly more elaborate. So without taking much time, let me quickly scroll through the discussion we had last time on electric and hybrid electric vehicles. Then we can move on to today's component. If you have any question at any point of time, you can raise your hand or type it in in the chat window. So we started our discussion on on electric and hybrid electric vehicles with few broad questions. First one being, what are the requirements of an automotive powertrain, and how could one size components of an electric vehicle and a hybrid electric vehicle to meet the vehicle performance requirements? So performance requirements were given in terms of maximum acceleration, maximum longitudinal speed, gradability, fuel economy, and electric vehicles and plug-in hybrids for them in terms of range. So we discussed 3 components. First being powertrain, that includes everything starting from your prime mover and ending it at the wheels. The driveline component, which driveline is a set of components which excludes the prime mover and includes everything after that. That would include essentially the transmission and the final gearbox, if any, and your wheels. Then you have the transmission, which uh, typically refers to a primary gearbox. So this is an illustration where you can see prime mover, which generates some torque at omega tau p and omega p at omega p, which goes to a transmission, which includes your primary gearbox and final drive, which goes to the driven wheels, giving you force at the wheels and vehicle motion at some velocity v. So we discussed few issues with the IC engine and it kind of highlights why do we need gearboxes, because IC engines do not have a large range with really good performance. So to take it closer to this ideal traction parabola where tractive force and longitudinal speed are plotted, we would use gears in order to match it as close as possible, whereas the electric motor allows us to go to ideal traction parabola with minimal add-ons. So we looked at various engine efficiency losses, in what all places we are losing out. That is heat, parasitic losses, and rolling resistance and wind resistance, and even your drivetrain losses. So if we were to compare IC engine and hybrid electric vehicles, considering your fuel source as 100, we discussed last time that total energy remaining in case of IC engine was around 16, whereas in HEVs it's 66, indicative of uh, significantly higher efficiency. Then we took a look at few history of electric vehicles, and various vehicle powertrain types, them being internal combustion engine, then electric, hybrid electric, and plug-in hybrid. In electric, we had pure electric as well as EV with a range extender, which essentially includes a small engine which can recharge your battery and extend your range. Then you have series and parallel or series parallel hybrids, which uses engine as well as it will use engine as well as the electric motor in different mechanical combinations to drive the vehicle. Then we looked at several types or how the components are placed and how do they interact to get you the type of electric vehicle or hybrid electric vehicle. And finally, we ended with discussion on hybrid types, where we defined a degree of hybridization, which essentially takes you from 0 to 100%, and it discusses how much of power is coming from electric vehicle and how much of power is coming from the IC engine. So that was our end of session 1 last time, and today we will be discussing a few things about these motor characteristics. So if we were to look at motor characteristics uh, of a typical electric motor, we can see that first gives you a large value of torque at even 0 rpm or 0 speed. Then it gives you constant torque up to a value where your power would increase uh, as you increase the rpm, and this particular speed at which this kind of switching happens is called base speed. So at base speed, the constant power region starts. That means the motor will not be taking any more power, and in terms of power, the motor has saturated. So with increase in rpm, we will start looking at decrease in the torque produced by the motor. So yeah, the base speed is essentially the speed till which constant torque region extends. The maximum torque is obtained up to this speed and then it drops. So we can define speed ratio for a motor as ratio of the maximum motor speed to the base speed. So if we were to look at the maximum torque which is obtained by the motor, we can think about it. So in this particular slide, we are saying that we had already developed expressions for maximum tractive forces. I think this we will be doing when we are doing braking and traction somewhere around that time, I think in week 7 or week 8. So we will discuss this at that time. The maximum torque that the prime mover or the motor needs to provide to obtain a tractive force is given here as F max into Rw divided by Nt into eta t. So uh, where F max is the maximum force you would like for the vehicle to move, then Rw is the radius of the wheel, and we'll look at Nt and eta t during transmission. Eta t is the transmission efficiency and Nt would be the uh, transmission ratio. Uh, let's consider that for time being. So if you look at the maximum longitudinal speed, it is given by this Vmax as equals omega max into R bracket 1 plus lambda divided by Nt, where omega max again is the maximum uh, rotational speed and lambda is the wheel slip ratio. So this lambda is defined as R omega minus V by V, or during braking, and during traction you can define it as V minus R omega by V. So if we take the torque, corresponding power and corresponding torque at this point, it will be given using these expressions. So if you look at this power expression, first thing we are looking is 1 over eta t originating from the transmission. Then if you look at the terms in the bracket, we have Fr into W, which is rolling resistance of the tire, and W is the weight on the tire, and half rho CD into AF into V square is the aerodynamic drag. So this is the force multiplied by the velocity.
Good evening, sir.
Yes. All right. So yeah. Do you have any questions? So then we can also take look at torque by substituting the force term from this expression here. Our next requirement is on the gradability. Gradability is indicative of the steepest gradient that the vehicle can climb at a lower speed. So gradability is defined as it is given by tan theta of s. So if you want to climb your vehicle uh, on a grade or on a ramp which has angle theta s, its gradability is given by theta s. This is one of the regulatory requirements for a vehicle to get certified for real world use, and the power required in this case would be higher than the power required for in case where the vehicle is expected to move on a flat road. So in this case, while moving the vehicle, we have to overcome the rolling resistance force, that is Fr into W given here, the aerodynamic drag, along with it a component of its weight given here as W into sine theta s. So when compared to previous case, we are adding one more term in the forces to overcome, which is W into sine theta s. So then the same change would be made for the torque as well. So the maximum torque which we are getting from the motor and the maximum power should certainly be higher than P grade and T grade for requirement of gradability. So say if you have 17% gradability, whatever is the theta is corresponding to that is tan inverse of 17 by 360, would, so 17 over tan inverse of 17 by 360 degrees would be the grade we want to climb, and the power from the motor as well as the torque should be higher than that. So if we desire to go from 0 to Vf, the vehicle longitudinal speed, in a time interval of Tf, the corresponding motor traction power is found using this term. So here we are essentially neglecting most of the resistances. So going from 0 to Tf, we are taking gamma into m into 0 to Vf dV by Ft. So this force we would write as tractive force, and after solving the integrals we will end up getting this expression for the power. So here we are breaking down the integral into two parts, 0 to Vb, that is the time where we are linearly increasing the power as the vehicle speed increases, and from Vb to Vf, where we are looking at the constant power mode where the torque decreases. So if we are considering the effect of aerodynamic drag and rolling resistance, the prime mover power required for acceleration is given using this expression, uh, where we are adding the rolling resistance term as well as the term from aerodynamic drag. So, so we have a problem which we can try out. We have to consider these things, and we have to calculate the power required for cruising the speed, power required for climbing a grade at 15%, and the transmission ratio for achieving this. So I think if we use all these expressions, we can solve these questions. But what I would rather like to talk about today is regenerative braking. In regenerative braking, the idea is to convert the kinetic energy of the vehicle into electrical energy by using traction motor in the vehicle as a generator. So this regenerative braking capability is only available on the driven wheels, that is the wheels which have uh, are having a motor connected, and certainly it alone cannot provide the desired braking torque or the deceleration required, and hence in such a situation we would uh, do something called cooperative braking, that is by involving friction braking as well. So as you know, we have friction brakes on IC engine vehicles. Again, we'll be taking a look at it in the brake section. But today we can have some more discussion on regenerative braking. So this, so the regenerative braking needs to be regulated along with friction braking so that we can have blended braking situation. The factors which affect the regenerative braking include battery state of charge, vehicle speed, driver's demand, uh, and a few things if any. Then braking blend out is withdrawing the regenerative braking from driven wheels and meeting the brake demand only through friction braking. So let me pull my notepad here to discuss a little bit more on regenerative braking. So the idea in regenerative braking is to recover the energy that would have been lost during use, using friction brakes. Okay, so say if my vehicle is traveling at uh, 25 meter per second speed, and I have a truck with mass of uh, 16,000 kilograms. Okay, so the kinetic energy of the vehicle would be half into m into v square. Okay, so let's calculate that. 8,000 into 25 into 25. Okay, so this much is our kinetic energy. So if we were to dissipate this energy during braking, we may or may not will not be able to certainly use the traction motor as generator alone. So let us see what are the requirements from regenerative braking. First requirement is mm, we want to recover the energy. Second requirement is retain the vehicle stability. Okay, so this retaining, so we have two different objectives. So let me point out to the aspects which this relates to. Your energy recovery aspects would relate to the battery system. It would relate to the being motor being used as a generator, and it would also relate to the power electronics. Okay, your vehicle stability aspects would relate to the vehicle and the environment. By environment, we would specifically mean the Connection issues, just 1 minute. Okay, I think I am live. Alright, so when we are discussing vehicle stability in terms of environment, we have tire road interface. And in the vehicle aspect, it would encapsulate all these 3 points. Alright, so understanding all these things, let's try to quickly look at how do we characterize vehicle stability. So vehicle stability can get compromised in case of wheel locks. Okay, and this is where it connects to the idea of anti-lock brake system, which prevents the wheels from locking. So, wheel lock can result in difficult scenarios like you may lose steerability if your front wheels have locked, and your rear wheel lock can result in undesired yaw motion, which we would like to avoid as it may lead to a vehicle moving out of the road or may result into some collision. So let's try to understand and draw a block diagram of various systems, and let's ask which component may ask what kind of questions to us while designing a regenerative system. So let's consider an pure electric vehicle. So you have the motor, this is connected to the wheels, which is connected to the power electronics, which can drive the motor or can take power from the motor. So I'm drawing the energy flow with arrows because in case of regen. Now we have the motor, the power electronics, and let's put the battery. So let me introduce one more layer as BMS and then a battery. EMS's battery management system. So in this battery management system, uh, so we have like now four components, and we have vehicle level requirements. So my vehicle requirements would be to ensure vehicle stability and to respect the driver's demand. So first thing is, so what is the objective in this case? So let's write down the objective. We want to recover maximum amount of kinetic energy of the vehicle while doing two important things. While meeting the driver demanded deceleration and ensuring vehicle stability. All right. So this is what our objective is. So if, as we discussed earlier, if the driver demanded deceleration is not achievable by full capacity of our friction brakes, then full capacity of the motor, then what should we do? Then we should incorporate friction braking. In such a case, if the friction braking needs to be incorporated, we have to ask, so we are asking first question, is the demanded deceleration achievable by the is the demanded deceleration achievable by the regenerative brakes alone? If it is yes, then just use the regen. If the answer is no, include friction brakes. Okay. Then if in case If in case the friction brakes are required with regenerative braking, what can we do? So, how much of requirement is fulfilled by which type of braking? So here we have two choices for braking. First is regenerative braking and second is friction braking. Since the demanded deceleration is cannot be achieved only by regenerative brakes, we would like to utilize friction brakes as well. In such a case, we are asking how much split should be between the two of them. And then, of course, there will be a natural question on controls like how are we going to achieve these things? But meeting our simple objective of recovering minimum maximum amount of kinetic energy of the vehicle while meeting the driver demanded deceleration and ensuring vehicle safety. So these two things alone will be I mean, we cannot directly achieve it. Each of the component in the system would have a say in how would this process follow. So uh, your motor will be limited by how much power it can take. So there will be a maximum power limit on the motor, which will correspond to so the motor will have maximum power limit, which would translate to a maximum value of achievable braking torque by the motor. Next to the motor, we have power electronics. There may be such a situation where the power electronics is not capable of taking in all the current or all the power which the motor is generating. So, in such a case, there may be a cap on maximum power the power electronics module can process. So, that is another challenge. Then we have battery along with our BMS. So, we can consider this as a single unit if you want to lump it up. Alright, so battery will have its state of charge. State of charge is essentially the percentage of battery which you have been hmm, Okay. State of charge is essentially the percentage of battery we by and large look at our phone. So it's slightly more complex, but indicative of the same. How much battery has uh, charging and how much of it can we charge. So, for example, say if your SOC is 80%. If the SOC is 80%, then you can hold 20% more. You can charge the battery by to the remaining capacity of 20%. Okay, and again, if it has any charging power limitations. So if you cannot give more power than a limit, it does not matter if your motor or your power electronics is able to take up that much power. If you are not able to utilize if you are not able to put that power in the battery, it has to be then dissipated by the friction brakes. So as you can see, it's not directly that straightforward in principle also that we can just expect the motor to run in reverse mode and charge our batteries. There are various components, each one of which would play a role, and its level, it would, I mean, like the level of charge we already have, the current already which is flowing through the motors, will all impact what we can do or how much power we can recover. So this is all about the thought process which can go into development of a regenerative braking module for power electronics. For pure electric vehicles. It's also applicable to hybrid electrics. So once we come to braking, we will revisit the idea of regenerative braking with more knowledge from uh, the brakes module, where you would learn many things about friction brakes. So let me go back to the slides now and discuss few more things. So we were having a discussion on regenerative braking, and we took a look at regenerative braking in terms of what its objective is, what questions we should ask to meet our objective, and how various components in the electric vehicle would affect the regenerative braking. So, coming to the cooperative braking strategies, first is series cooperative braking strategy. So here the braking demand is initially met through regenerative braking on the driven wheels, and further demand is met through friction braking. So in this particular case we are using both, but first we say we will use regen and next we will use uh, the friction brakes. So in slides you can see that from up to point B we are using so we have something called ideal brake force distribution curve, which plots the braking force on the front wheel and the rear wheel, and we would like to be as close to this curve as possible to ensure stable braking. Then from point B to C we are now using friction brakes. Similarly, now in terms of parallel cooperative braking strategy, regenerative brakes is applied on the driven wheels as a proportion of total brake force demanded by uh, the driver. So this is limited by maximum possible regenerative braking force, which is taken as some factor of gamma into Fp. So there is more potential for higher energy regeneration in series right, in series cooperative braking, but it requires us to have more sophisticated electronic brake control system. Okay, so you can see in this case, both of the brakes are coming in together. Yeah, so the question we are ending for the regenerative braking topic is that how do we distribute the braking effort between friction and braking? Sorry, between friction brakes and regenerative braking. So, second question is how does it affect the stability of the vehicle and how does it integrate brake blending with wheel slip regulation? So, we would discuss what wheel slip regulation is during the braking point or during the discussion which we will have on braking aspects. So I think that is the end of session 2 on electric vehicles. In next session, we will take a look at few things on uh, batteries. So what are various types of batteries and what are their limitations and so on. So if do you have any questions about what we discussed today, we can have those coming in now.
Good evening, sir.
Yes.
Sir, which is more efficient, sir? Regenerative braking or the frictional braking, sir?
So which is more efficient?
Yeah.
Efficient in what sense?
For example, a moving car,
Okay.
which is an electric vehicle that is moving on the surface, and we want to stop that vehicle.
Mhm.
By applying the brakes.
Mm.
So, which system will be better? So, like the frictional one or the regenerative?
So see, regenerative braking in your electric vehicle will help you recover some energy that will go into the
Okay.
battery. Okay. If the
Okay.
energy is going into the battery, then what would happen is that it would help you increase your range, correct?
Yeah.
So if your demanded deceleration is not too much, that is, if you have not pressed your brake pedal a lot,
Okay.
okay, in such a case, and your vehicle speed happens to be high enough, can you then the brake system would ask a question, can I fulfill your demand completely using regenerative braking? So the first choice would be regenerative braking in a sense that you will get maximum energy back.
Okay.
Okay, you will try to get
Okay.
maximum energy back. But if in case your demand is not getting fulfilled by regenerative alone, then we need to bring in friction as well.
Okay.
Okay, so if it is a choice between vehicle safety versus regenerative, we would prioritize the vehicle safety and give you the demanded deceleration regardless. So, how exactly to do it would require some more details on brakes, I guess.
Okay. Thank you, sir.
Yes. Yeah. Any more questions?
Sir, what about the next break that
What about next? Sorry.
means, sir, another break like disc brake means that is not in this.
No, I did not get you. Can you repeat?
Sir, in electric vehicle there is disc brakes.
Acha, disc brakes. Okay. Oh, are you asking that?
Yes, sir.
You can have disc or drum brakes, depending either is available. So some of the vehicles will have uh, disc in the front and drum in the back. Some of them will have all disc brakes, depending upon the cost of the vehicle and all. By and large, most of the vehicles you look at will have either all drum or front disc and rear drum brakes. Uh, right. So yeah, that we'll discuss why it is so more in the brakes part when okay.
Sir, a regenerative brake is disc brake or another brake, sir.
No, regenerative braking, what you do is you use the motor inside the electric vehicle. So you have a motor in your electric vehicle which you use for driving. Okay. Instead, the same motor you are using as uh, the same motor you are
Brake.
using as a generator. Okay, or brake. Right. If you are using it as a generator, that means you are converting the motion of the energy in the motion of the vehicle to electrical energy. Okay.
Thank you, sir.
All right. Any more questions?
One doubt.
Yes.
So if we compare the like hybrid versus full electric,
Okay.
so uh, comparatively, which will be the full efficient in terms of cost and performance? Whether to have like I'm concerned about the large like full hybrid, like strong hybrid.
Okay.
When you take a full hybrid where you have a good amount of decent motor power so that you can even drive the vehicle. So
Mhm.
which will be more efficient, whether full electric or strong hybrid?
So, full electric will give you. So, see, there are a couple of aspects which we can think of. So, in case of a full electric vehicle, if your battery is out, people are suffering with range anxiety, which, as a buyer,
Hmm.
if you were to consider that if my battery runs out, so what can I do? And you have to plan your every activity around it. So, to get rid of it, you can have strong hybrids. Even the one benefit of strong hybrid is that you do not require that huge of a battery because there is also an engine to support you. But in terms of cost, we are increasing the complexity of the system, right? If you were to look at a strong hybrid, it will have components of an electric vehicle as well as components of a, a conventional IC engine driven vehicle. Because of that, the complexity increases. But in terms of efficiency, you can certainly benefit by a strong hybrid in terms
So only
of
thing is
your
the
flexibility.
fear of range, or since electric vehicle is not matured, that
Mhm.
fear might go when you are in full hybrid, correct?
Yeah, so that's what. So if you look at the offerings, recent offerings like Rider and all, I think from
Mm.
Toyota, they are good hybrids which gives you best of both worlds. In that
Mm.
particular case, the battery size required is also like 1/5 or 1/7 is what I heard. Okay, than a normal electric vehicle.
Mm.
That means you can use lesser batteries for most of it. Whenever IC engine is not efficient, or if you are going for smaller trips, you can utilize your battery, say like less than 20 kilometers trip. By and large, it will give you 60 to 100 kilometers of range on pure electric mode, and then you can always use your engine. So it kind of tries to give you best of both worlds when you are in city driving conditions on shorter ranges. It by and large acts like a pure electric vehicle, but then when you need a vehicle which can take you long distances without much of an issue, a strong hybrid would uh, give a bigger right, a larger flexibility in that sense. So hybrids do allow you to operate the motors as well as the engines at the best of their capabilities or in their best region of operation.
Sir, I have a doubt.
Yes.
Can you tell me how does multi-level region braking works?
Sorry, can you repeat?
Multi-level regenerative brakings.
Okay, can you, explain multi-level regenerative braking?
Yeah,
Because,
like different modes of regenerative. Like if we use level one, the braking will be much lower,
okay,
and at higher level, the braking will be much higher.
okay, so you are asking how would the braking process go about depending upon the driver's brake input. Is that what you are trying to mean?
No, actually, how can like in modern vehicles like in Teslas and all,
Okay.
like one pedal driving and all. So
Uh-huh.
how can like from one like we can get different braking effect from a single motor.
Mm-hmm.
Like how is
Yeah,
it possible to?
I think his question is like in the electric car, we
Uh-huh.
have a, three level of regeneration. Like user can choose the regeneration level. So
Okay.
if you choose region level 3, that will
Uh-huh.
be very aggressive region. So you will get
Okay.
more energy back. But if you like, if the driver feels like there is more aggressive region and he's feeling discomfort, he can select the level one. So now every OEM is giving the choice to user what
Oh.
level of region he wants. Level one, level two, level three. That is like small button is there in the steering wheel.
Oh, okay,
So the
okay.
more the level, the more the aggressive will be the region. Like it will almost stop the vehicle. If you go level three, it
Mm-hmm.
will even without brake, it will try to stop at some distance.
Okay. So, okay, now I get the
That is there
different
in
level of braking.
that is that is there in Kona, and I think in Mahindra XV4 also they are
Mm-hmm.
putting it. Let allow the driver to choose what level of region he wants.
Okay. So, and what was the question? Can you repeat a little bit? Now I'm more
Yeah,
clear,
how does
clear.
this regenerative, multi-level regenerative works?
This question is how it works.
Oh,
If I try to choose level 3,
uh-huh.
what exactly happens? Like there is like now if I put level 3, that means it will produce more current or more energy from the motion, and it
Mm-hmm.
goes to battery pack. How that system operates
How that's
at
oh,
the
see, as a control engineer, what
uh,
I would, let me think aloud here. I'm not telling how exactly it works, but let's think together to see how it can potentially work. Right. One way can be that you, for example, if you are working with you can change the power you're drawing from the motor itself. Okay. So if it is an induction motor, again for discussion, then I will change my stator current. Uh, I'll reduce my stator current so that the total brake torque I generate or the total power I recover from the process is lower, right? And that by and large gives me even an analog level control rather than three discrete mode of low, medium, and high. Like in what, how much power am I willing to take from the motor? So we can cap it at that one particular instance itself. So for example, if you are saying I want level 1 of braking, then I will keep my current limitations to certain, say X ampere. If you say 2 level 2, I'll make it say 2x, and if you say level 3, I'll make it 3x. So in a very simple manner, this kind of systems can be designed, again depending upon the, right, these things by and large are backed with market surveys and how much deceleration people are comfortable with while driving, and then that ends up dictating the design. But the implementation aspect of it would by and large come from the software setting, because anyway you are changing one switch. I hope that slightly clarifies.
Yes, sir. Okay.
Okay,
Thank you.
thank you.
Hello, sir.
Hello, yes.
Sir, do we cover eddy current braking in the course?
uh, the current braking, not much familiar to cover that for you. I can assure you that the sessions on ABS will be really good. That is one of our core strength uh, as a group, and that's what I have been researching on from past 5 years roughly.
Okay.
So yeah, anti-lock brake system is something which we can discuss at length.
Okay. Okay.
All right.
Thank you, sir.
Okay. Yeah. So do we have any more questions on what we discussed today? Of course, you can always ask for more questions. Now, what I want to do is pull up the notes on the supercharging and combustion in spark ignition engines. Do you people have any questions in that? Uh, we can perhaps discuss those things. Yes. Uh, yeah. Do you have any questions on these aspects, or uh, shall I quickly summarize this lectures in few minutes? Uh, I think let's quickly go through these concepts, and then if you have any questions, we can have a discussion on it, or we'll see how it goes. So during the engine performance, we looked at something called brake power. Brake power is the power at which is what you get at the end of your wheels. It is defined as some constant into BMEP into Vs into N by 2. So this brake power can be increased by two ways. First is by increasing BMEP, that is increasing the pressure at which air or air fuel mixture is introduced into the combustion chamber, and second is by increasing N. So the process of increasing this, increasing the pressure uh, at which air fuel mixture is introduced in the combustion chamber is called supercharging, and a device to do so is called a supercharger. Right. The benefits of supercharging are as follows. The density of intake air increases because we are increasing the pressure. So as the density increases, the mass of air taken into the cylinder increases, resulting into improved uh, volumetric efficiency. Since MEP increases, power output would also end up increasing, which would give us more thermal efficiency, and consequently we can obtain more torque or power from the same displacement volume. So superchargers can be classified as mechanically driven superchargers or turbochargers. The mechanically driven superchargers are driven by the engine crankshaft, and it works every time the engine is active. On the other hand, the turbocharger is driven by a gas turbine, which is in turn driven by the exhaust gases coming from the engine. So if we look at the schematic, the exhaust gases would come in, shown as red here. It would go into the turbocharger, and it will drive a turbine. This turbine uh, extracts some energy from coming exhaust gases and leaves the exhaust gases to atmosphere. And on the other side, it also pulls in the atmospheric air and pressurizes the same. So the deal with turbochargers is that it requires some minimum sufficient amount of vehicle speed, which corresponds to some level or threshold of the speed of exhaust gases, so that the turbine can be driven. So this gets activated at above certain speed, and it's not always active. So we get the hot and pressurized air, it gets cooled using the intercooler. This would decrease the initial temperature and improve our efficiency, right? And this pressurized air is then fed into the inlet valve. So that is the idea behind supercharging. Then we looked at various stages of uh, combustion in combustion engine. So in a spark ignition engine, we have a spark plug, the inlet valve, and the exhaust valve. When the air fuel mixture is compressed, the spark plug generates a spark, which essentially uh, results in the process of combustion. So if we look at the crankshaft uh, angle, and if we look at the pressure, we can look at this particular curve. So the motoring curve is the curve drawn at in the case where there is no combustion. So from as the crank rotates, the pressure starts increasing as uh, the volume starts decreasing. Then from point A is where the ignition starts, right? And point B is where the combustion starts. So there is a little bit of lag between the growth and development of a self-propagating nucleus of a frame. What do we mean by that? A spark generates a small nucleus of flame, and it propagates out in uh, the cylinder. So okay, point B. Uh, at point B, the combustion starts. So this point E is where we reach the top dead center, and from B to C, we are looking at propagation of flame. That is, the flame is moving. Okay, so just give me 1 second. All right, so yeah, from B to C, the flame propagates, and from C to D, there is afterburning. And this process keeps on continuing. Then we discussed about knocking in these engines. So what happens is when we start a spark, uh, due to combustion, the gases starts expanding. Okay, with this expansion, the flame also propagates in one direction. Hello? Okay. Yeah. So on one side, the flame will start propagating and the gases would expand. At the same time, at some other point in the cylinder, there can be some level of self-ignition because the temperatures have increased much more now, and this self-ignition also starts a flame front. So it's like you can look at a flame front and consider that flame front as a wave, and then there is a collision of two waves. If there is this kind of a collision, we would look at some pressure pulses in the engine. Now these kind of pulses would result in damage to your engine because this happens time in and time again every time you pass through all your four strokes. So we are natural to ask, if we do not want to damage our engine, what are the questions we can ask? We are asking what are the factors that influence the knocking in SI engines, and how does one quantify anti-knock properties of the fuel? So answer to this came in as anti-knocking fuels. So these are the factors which we discussed quickly. The compression ratio, if we increase the R, thermal efficiency would increase. But we can say that if the temperature at the start of ignition increases with increase in R, this would imply that there is chance of knocking with increase in the compression ratio. So the range of R in SI engines is limited by knocking. Then there is mass of inducted charge. Increasing the mass of inducted charge increases in tendency of knocking. So if you are putting in more fuel, there is good chance that this would happen. Inlet temperature also would play a role. Increasing the temperature would increase tendency for knocking, and hence we should be careful about supercharging as well. Then there is retarding the spark plug timing. So we would adjust the spark plug timing in such a way that it reduces the uh, knocking tendency, but that would also result in lower power output. So increasing the flame speed would decrease the tendency of knocking, and decreasing the engine size would decrease. But here in such a case, we need to be we are looking at conflicting requirements. On one side we are asking for more power, and on the other side we are saying let me also decrease the engine size. So these things need to be balanced. So there is something called as an octane number, and this is indicative of anti-knock characteristics of the fuel. So the petrol which we get uh, is mixture of heptane, isooctane, and now we also have ethanol added to it. But the addition of this isooctane, the addition of this isooctane is essentially what decreases the characteristic of knocking. Yes, By the way, there is an excellent video on carburation which I am sharing with you all. Kindly take your time and watch it. It will show you every single detail. Uh, okay, so I would request you to watch this video. It's going to be, I'll show you on this, show it on the screen as well. It's called How Does a Carburetor Work? And it will show you a transparent carburetor with uh, yeah, so it will show you a transparent carburetor at a very slow motion, so you can look and understand each and every process happening in the carburetor. So uh, do we have any questions from people at this particular point in the aspects of combustion or anything else? Hello?
No, sir.
Okay. So because most of these things are already covered in the classroom and by and large they are theory, so I don't know what more to discuss than what you already know. Yes, Raghu, you can either talk or you can text on the. Yes.
Sir, if we increase the compression ratio, we'll get more power only now. So how the knocking will occur?
Okay. So let me scroll up little. Okay. How would the knocking occur if you are increasing the compression ratio, right?
Yes, sir.
Yeah, so if we increase the compression ratio with increasing pressure, your temperatures are also bound to rise. Okay, uh, at in an overall sense, if your temperature is higher, the tendency for self ignition after the spark has been ignited is going to go up. Since this tendency goes up, uh, tendency of sorry self ignition goes up, there is a higher chance of you having two different wave fronts. And if you have two flame sorry not wave fronts, flame fronts, if you have two flame fronts, uh, the possibility of collision and hence knocking increases.
Okay, sir.
All right. All right, so any other points, any other questions? Yes, we have posted few new videos. Let me go to course and show it to you. If you go to the announcements section, Uh, these are supplementary tutorial videos which you can follow with calculations. So you would look at all these engine performance, what do I say, engine performance matrix being calculated for an engine. And we'll also, in part first of the three parts, we'll show you the engine disassembly as well. So I believe that these videos will be helpful to you. They are supplementary course material uh, which was recorded after the NPTEL sessions. So I recommend all of you to go and take a look at these videos. Then yeah, as we were discussing, coming to the about the course section. So next week would also by and large be on the theoretical aspects of combustion in compression engine, that is the week 4 part, carburation and fuel introduction systems. You can check in the link, check in the messages. I have sent you a link for a video on carburation. What we would recommend is what I think we should do for these in-person sessions is that we discuss the things which are not part of this and discuss few more problems. So we will by and large dive into automotive powertrain in our next tutorial session, and we will cover things up so that your homeworks from week 5, week 6 and so on gets synchronized. So if I go to courses and so the week 5 quiz is due on the 1st of next month. So, and we will be meeting on 27th. So if you have doubts in these points, we can discuss, or we will start moving on with the powertrain, which is more involved and mathematical in nature. So we will be slightly taking a leap in this case so that we can catch up with automotive clutches, transmissions and so on as you watch the videos. And then we will delve into the brake system. So I think that is all I have for you people today. So you can ask me more questions because we have time. And if you don't have, yes, Raghu, you can ask.
Sir, still it's not clear. If you increase the compression ratio, the
Okay.
temperature is going to be increased.
Uh-huh.
So it's going to self-ignite by its own temperature.
No, it
So
won't.
after the burning also, if you apply the spark, there is no use of that only now. So how this will happen?
No. So see, let's try to understand the chain of events. Okay. First, we have a spark. The spark results in initial flame formation. Okay. So if you can look at this particular diagram here where my pointer is, a spark happens, the flame front travels in the front, and that flame front also starts pushing the rest of the unburnt air fuel mixture towards the wall, increasing the temperature as the pressure is increasing. And at certain point, because one combustion process is resulting in more compression, the temperature may get closer to self ignition, and it would catch fire.
Okay, sir.
Okay, so I hope that slightly helps.
Yes, sir.
Okay, yeah, you can ask more questions. Uh, Hello, yeah, any more questions? I think if we have no further questions, can we close the session?
Sir, one general question. Can I
Okay.
ask?
Yes, yes, absolutely.
Sir, in the future, there is completely going to be an electrical vehicle, or
We'll find out as the time progresses. Electric vehicles are getting good. Right, they are much easier to maintain. Their initial cost of ownership is higher. So, as we move forward and figure out the cost models, we should be good to go. So, the problem is slightly on the economics and less on the technical front. But as the fuel prices keep on increasing, we are bound to see a complete transition to electric for most of the things.
okay, sir, if IC engines is not there, if we use the electrical vehicle, then there is no use of flywheel or propeller shaft or
There is no use of.
flywheels and propeller shafts.
Yeah, so there are now in-hub motors also, right? Sorry, so in-wheel hub motors, which eliminate almost all of them, all of the components, and it improves mechanical efficiency because there isn't any mechanical component in between. So, so that is something which we are looking forward to. But again, it's by and large at what price point are people willing to pay for what range and everything. So it's
Okay,
more
sir.
of a complex problem than a technical problem, I can assure you of that.
Okay.
All right. So yeah, any more questions? Okay, so I think let's close down the session. We'll meet next week. We'll complete our discussion on batteries, and then we will take a look at other things like, and we'll take a look at other stuff also. And that includes, let me summarize quickly, discussion on some control systems and automotive powertrain. I don't know. So let's see how it goes. All right. Thank you for joining. I'll see you next week at 6 o'clock. Thank you very much.
Thank you, sir.